Hi, my name is Banan. I'm an astroparticle physics student at the University of Zurich, and I love condensing physics into bite sized pieces that everyone can understand and enjoy. Because the universe is a really cool place, and the more I learn, the more amazed I am. And I've got my friend Dylan here today.
Hi, I'm Dylan. Uh, I've met Banana at Durham, and yeah, she's gonna teach me a little bit about astrophysics, a little bit about me. I used to be a swimmer and water polo player. I'm now CEO and co-founder of Toutix, and currently living in London. So excited to be here. Thank you for having me, Banana.
It's nice to have you here. So, two of the biggest mysteries of the universe are dark matter and dark energy. What is the first thing that pops in your head when you hear those words?
I feel like when I hear dark matter, I'm thinking like an evil character in a Marvel movie, or dark energy. I feel like someone's gonna try and like come take my soul from me, which is definitely not right, but that's just like the first image that comes to my mind. Someone's trying to come like attack me.
So more science fiction than something that's actually real.
Absolutely, yeah, yeah.
So did you know, so this is a mind-blowing fact, right? Did you know that about 5% of the universe is made up of regular matter? So things we can see, like stars, planets, people, that's all made up of regular matter, and that only makes up 5% of the universe. And about 27% is dark matter, and 68% is dark energy. So most of our universe is actually made up of these things that we don't even really know that much about. It's crazy, right?
So we don't know all that much about them, but they take up like all the space in our lives.
Yeah, so it's like imagine if you're in a room that's full of furniture and you can't see it, but you keep bumping into it so you know it's there. That's what dark matter is. It's we don't know that we can't see it, but we know that it's there because it has the effect of something that takes up space, but we don't see it. So we're like, there's a big question mark.
Like the Harry Potter invisibility cloak. You're walking around bumping into things. Hagrid's trying to avoid you. That's
Yeah,
crazy.
actually.
So it's just chilling there and like you can't see it, but you just know it's there.
Yeah, literally. So how do we know it's there? And that's where physics comes in.
Like Santa Claus, I
Um,
guess. Seeing is believing, believing is seeing.
okay,
Yeah.
so we call some. Okay, so we can say dark matter is the universe's invisible glue. Okay, dark matter it
Why is
doesn't
that?
emit. What
Why
do you
is it the
mean?
universe's invisible glue?
Well, you have to wait to find out.
Okay, okay, okay.
So dark matter it doesn't emit, reflect, or absorb light, right? And like I told you, we can't see it directly, but we know it exists because of its gravitational effect. Because, like I said, it does affect the space that's around it. We just can't see it. So another like sort of helpful metaphor that might help you understand is imagine you have a merry-go-round like a carousel and it's spinning super fast. And it's spinning so fast that you would expect the horses to fly off, but they're not. Okay? So what is this thing that's keeping them in place? What's bolting them down to the ground? That's dark matter. In galaxies and stars, the edges move so fast that they should escape. The stars should escape the galaxies, but they're not. And it's dark matter that's kind of keeping them anchored there. Are you just trying to wrap your head around everything I'm
Yeah,
saying?
yeah. You got to remember you're speaking to someone who has negative knowledge in physics. So I'm trying to wrap my head around this and comprehend it in a way that makes sense to me. So you said it's like a merry-go-round and like the horses are just like levitating, but it's going super fast that you expect them to just go flying off, but like because you can't see it, that dark matter is kind of like the pole that keeps it tethered to the ground.
So a little bit. So basically, what I'm saying is, like a merry-go-round, galaxies spin really fast, and what we know
Mm-hmm.
about physics, what should happen is these stars are meant to fly out, but they're not. Something is keeping them tethered to the galaxy, to the inside of the galaxy, and that's dark matter. Same as if you have a merry-go-round that's spinning super fast, you expect the horses to fly out, right? But they're not. Something's keeping them bolted down.
So is dark matter like a really general term then, or is there is there a lot of different layers to dark matter, or is it like because if you're saying it's like a merry-go-round, right? Like it's like saying it's glue. right? Well, there's different like compartments to like how glue keeps it together.
Yeah. Yeah, so basically, we don't know what dark matter is made of. There are a couple contenders because this is something that we haven't even detected yet. You know, we just know that it exists. So there's a couple of experiments that are running around the world. There's a couple of theories as well. The number one theory at the moment is that dark matter is made of something called WIMPs. WIMPs is an acronym. It stands for weakly interacting massive particles, and these are like, I guess you can call them cosmic ghosts. So they're particles that have mass and gravitational influence. So they, interact with things gravitationally, but they don't interact with light or ordinary matter.
So you're calling the
Okay.
ghost a wimp. I don't know. I wouldn't really call a ghost a wimp. That seems like
Uh,
that's some bad voodoo coming your way, man.
that was a terrible joke.
It's
Okay, so
not
you
trying to be
might.
a joke, but like you're so you're trying to explain dark matter and like you're explaining to someone who thinks it's science fiction. So now you're calling dark matter again. You're calling a ghost a wimp. So I feel like that just like that's not boding well for the karmic cycle of this like exercise here, right? Like if it's someone who thinks it's like dark energy and like not the scientific way, but like a Marvel like metaphysical science fiction way, then calling a ghost a wimp is gonna be like, oh no, like that's not what you're supposed to do in this scenario.
Well, yes, but as physicists, we're always complaining because nature is not kind to us. You know what I mean? In the sense where it has not made things easier for us to understand as physicists. We try to, every time we think we know everything, we realize that we actually know nothing. You know what I mean? The universe is such a vast place and there's so many mysteries. And for sure, the universe has not made it easier for us to understand why it behaves the way it does. And that is both terrifying and very interesting at the same time. That's why it's important. Like these sort of things are important because people need to understand how complex, sophisticated, and beautiful all of this is. But most of the time, people fear, they're like, oh, but this is too complicated to understand. Like this is not, I'm a marketing major. I'm never gonna understand any of this stuff. But actually, it's super fun, and it's not. And this is not a dig at you because you're a marketing major, but because it's you might worry that it's not your field of expertise, so you become intimidated by it. You're like, you know what, I'm not even going to try to understand it. But that's such a shame because, like, I saw your face expression when I was talking about dark matter. You were impressed. You were, you
Intrigued, yeah,
realized
for
how cool
sure.
it is. Yeah.
I mean, yeah, it's good to like expand your mind into an area that you're not too aware of. But in the same sentiment, right? It's kind of like the way that, like how you said, it's not been easy for us as humans or you as physicists to kind of discover things about the universe. I think most people would probably take that because I don't think most people are. I think people are innately curious, but I think when you present them something that's far out of their scope, they prefer not to be curious because they don't want to be looked at as ignorant or wrong or not understanding it. So I don't think that it's something where you say like like we don't know it, so it's important that like like if someone's a marketing major, like they might be like overwhelmed by it. I think that they might just look at it as like because it's something they don't understand and because it hasn't been easy for us to find, someone may who's not curious may objectively look at it like maybe I wasn't supposed to find it. So I think that's kind of like the duality of that, right? It's not just the fact that you do want to uncover these things about the universe, but the reason people may not know about them or may not want to is because they may not feel like they want to. Some people use like their background as reasons not to want to dig into science as well. I think people can find that. And if it's kind of again, like I said, that duality of like you bridging your humanity to the parts of the universe that are unaware to us. So I think that's like pretty important. Um, yeah, and I think it's kind of like if you're walking across a bridge into the water, right? Like over the water to the other side of the land, right? Like, you know, if you've never been on that bridge before, if you've never been on a bridge before in general, then you're probably going to get a little bit worried, you know? And if you have a problem with water and you're scared of water, you might get a little worried as well. But you kind of just have to make that leap. And that's kind of how I'm looking at you explaining it. Because I don't think it's a lack of like that people would like people don't think the view from the bridge isn't going to be beautiful. It's just that they're scared of the water that's under it. They're scared if the bridge breaks. And I think that's where, people may not be aligned with what's currently going on in the space and such. So I think that's pretty important, if that makes sense, to give you like a duality of, a different perspective.
Yeah, I think it does make sense. And I think it's important to appreciate the fact that you were brave enough to, cross this bridge. And I think it's pretty cool that I'm the person that, is helping you cross the bridge and being like, oh, look at how beautiful the universe is. Please don't be intimidated. Like the bridge is safe. You know what I mean? I think that's pretty cool.
I mean, I think I was gonna walk across this bridge anyway, just because I'm a curious human, and I would get lost, so I would have to cross the bridge eventually, right? Like I think that's part of being curious and allowing yourself to explore new, different trains of thought, right? But yeah, definitely cool that you can show me some of the stuff and I can learn some of the stuff.
Yeah, so kind of going back to where we started, going back to dark matter, right? Because this is why we're here. You might ask me, so how do we know that it exists, other than the fact that there's like this, this glue that's keeping everything together, other than the fact that we keep bumping into it even though we can't see it. And this is like one piece of, I guess you can say, evidence that we have. So do you know when you're at a carnival or something and you look at one of these like funhouse mirrors and it kind of like distorts your reflection on the mirror? So like there's something weird that's happening with the light.
I'm not gonna lie, when you said Carnival, all I could think of was the song by Kanye West. But yes, I do know what you're talking about.
Yeah, so in physics we call this gravitational lensing. And what happens is when light from these distant galaxies is bent, it's bent by so let me go back. So what is gravitational lensing? This is when light from distant galaxies is bent as it passes by massive objects. Okay? The amount of bending is much more than what we'd expect if this was based on the visible matter alone. All right? So it's like there's something hidden, like there's a hidden mass that's warping the light, and it reveals the presence of something else that we can't see. So it's like if you're standing in front of one of these funhouse mirrors, right? And your image, your reflection is being a lot more distorted than it should be. Does that make sense? And that's called gravitational lensing.
So it's the gravitational lensing kind of just distorts like the image of yourself in this specific scenario. Like it kind of, it's like what's a real use case example of it? Real world use case, like real world example of it.
Yeah, so this is a real world example. If let's say you have a galaxy that's really far away and a galaxy that's like a little bit more in front of it, right? When we try to observe the galaxy that's closer to us, this galaxy seems to have like light that is a little bit distorted. When we measure that distortion, right? It is being caused by mass that is much heavier than the galaxy that is behind it, which tells us that there's a lot more behind it than just that galaxy. Does that make sense?
I think so, yeah. It's like if you're looking at something and you know there's something behind it, the light in front of it will look a little weird because there's something behind it, like trailing it. Is that what you're trying to say a little bit?
Yeah, but what I'm okay, so how can I explain this? So it's not just the galaxy that's behind it that's distorting the light, right? There is something else because that distortion is a lot bigger than what we expect it to be if it was just the galaxy. It's like these funhouse mirrors, right? If you're super tall, it distorts you in one way. If you're a little bit more round, it distorts you another way. If you know what I mean, if you're a little bit more skinny, it distorts you differently. So what I'm saying is, let's say you're like this really tall guy, but it distorts you differently as if you're not tall, but rather you're like really short. So it tells us
Okay.
there's something more happening. There's something more going on in the background than what we would expect because the math isn't adding up, you know?
The math isn't mathing. Yeah.
Another example is if you think about it as a magnifying glass. So if, let's say, these massive objects, the galaxy that's sort of behind the one that's closer to us, it acts like a magnifying glass, right? And it bends the light from distant galaxies. And sometimes magnifying or splitting the image into arcs or rings. So I don't know if you've ever seen pictures from like the James Webb Telescope or whatever, but they will sometimes have light that is like it looks kind of arched, like it. Do you see what I'm doing with my hand?
Yeah, you're
Yeah.
arching your hand, yes.
Yeah, yeah. So this is called cosmic magnifying, and this effect lets us see galaxies that would otherwise be invisible. So that's another way of thinking about it, not just the funhouse mirror, but this sort of magnifying glass in space. All right. So how do you feel about dark matter so far?
Yeah, I feel like I've definitely learned quite a bit about dark matter so far. I'm ready to jump in a pool and kind of just float around with nothing there because there it's like, oh, you said we can't see it, but we know it's there because of the gravitational pull. So maybe if I jump in a pool full of dark matter, I could just be swimming like some backstroke, do some freestyle, swim around, do a couple flip turns.
Yeah. And like even more surprisingly, this is only 27% of the universe. We still have another 6 to 8% to go, and that's dark energy. So we haven't even begun to talk about what actually is taking up so much space in our world.
You know what's taking up so much space in our world? Me. Some
So
no,
did you know that it's okay, not all jokes are funny.
well, you know what they say, one man's trash is another man's treasure, right? You are the astrophysicist here, so there may be a little bit lack of comical relief on your end. I've been told that I'm one of the funniest there ever was. So,
You're saying nerds don't know how to laugh?
I'm not saying nerds don't know how to laugh. I'm saying you don't know how to laugh. I think nerds definitely know how to laugh because I'm most
I
definitely a nerd.
I think I do know how to laugh, but it's okay.
All right, coach.
So did you know that the universe is expanding? Like, did you know that the universe isn't static?
I actually did know that the universe is always and forever expanding. It's like me when I go to the movie theater and I bring some extra snacks. My gut's always expanding because I'm having some good food. But
Yeah.
except imagine I did that every single day, and that's the universe.
Yes, because that's true. The universe is expanding infinitely. Okay. So for centuries, people believed that the universe was static, unchanging, and eternal. Okay? This idea was challenged in the 1920s by Edwin Hubble, who in the physics world is a pretty well-known guy. We've named a couple of things after him. And he discovered that galaxies are actually moving away from us. And this is how we know that the universe is expanding. So he measured this sort of like stretching of light waves from objects that are moving away from us. And this stretching showed that the universe is expanding. And so the best metaphor that I can use to sort of explain this is, imagine if you have a balloon, right? And it's not inflated yet, it's a balloon, and you draw using like a black marker, you draw a couple dots on it. When you start blowing air into the balloon starts to expand, but then every point is moving away from the other point at the same time. So not only is the balloon expanding, but the space between the points is also expanding.
So what you're saying is, while the universe expands, it's just getting further. That makes sense, I think, right? Like, I think that would make sense to me. Like, because if like I'm here and the current layer is 1 foot ahead of me, but then it's expanding, yeah, we're gonna separate. The balloon analogy was a good one for the listeners back home who need a visual. Good job, coach.
Okay, so how do we connect this to dark energy? How does this balloon analogy fit in? So for a long time, scientists thought that the expansion would eventually slow down. So like it would be like, oh, if you went to the movies, you had a couple snacks and you left. But the problem here is you haven't left because the expansion isn't slowing down. If anything, it's accelerating. So in the late 1990s, they discovered something shocking, which is that the expansion is actually speeding up. It's accelerating. And this acceleration couldn't be explained by visible matter or dark matter. So no, we thought, okay, the universe is made of visible matter. Using gravitational lensing and a couple other things, we realized that okay, 27% is made up of dark matter. But now we've discovered that not only is the universe expanding, but this expansion is accelerating. And now we're like, okay, we're lost again. Like I said, nature has not been kind to us. Every time we think we understand what's going on, it tells us, oh, by the way, it is not the way that you think it is. And
It
this is
hits
where
you
dark
with
energy
the
comes.
it hits you with the not.
Yeah, literally it hits you with the knot. And that's where dark energy comes in. It's the mysterious force that's driving this accelerated expansion.
Interesting. So dark matter is a catalyst to the expansion in this scenario, just like the caramel popcorn that you eat in the movie theater is a catalyst to your gut expanding. Is that what I'm understanding? Well,
Dark
technically,
energy is.
yeah, dark energy, not dark matter, yes.
Yes, there's a difference. Like I said, dark matter
Yeah, yeah,
is.
yeah. It's matter versus energy. I got you, I got you, I got you.
Okay, so let's put dark energy aside for a second and let's
Yeah.
look at the big picture. Okay, you still with me? You still
I'm looking at the big picture, at the movie screen, the world's still expanding. And yeah, I'm figuring it out. So tell me, let's see the big picture.
so we have a blueprint for, let's call it the cosmic blueprint.
Hmm.
Okay, because we like to add the word cosmic before anything to make it refer to the universe. So let's talk about the cosmic blueprint, right?
I don't know why, whenever I hear cosmic, I think of like, have you ever seen those TV shows or those movies where there's just like someone dancing, like moving their shoulders and like they have like a peace sign in front of their eyes and it's kind of like groovy. Whenever I hear cosmic, I think of that. I don't know why. Maybe
I
that's
think it's
such
because
a weird thing, but yeah, go ahead, sorry.
it's actually not. I think I know why, and it's because most of the time when they're dancing, there's a disco ball on top of their head, and that
Yeah.
disco ball, the kind of light that it's reflecting, kind of looks like, I don't know, kind of looks like stars, maybe. So it does give that cosmic vibe a little bit. Yeah.
Yes, ma'am.
Okay, so
That
going
does
back to
make
this
sense.
cosmic blueprint, and we call this the lambda CDM model. Lambda is the Greek letter. Lambda kind of looks like a capital A, and CDM stands for cold dark matter. So lambda is what represents dark energy. The cold dark matter, the CDM, is what represents dark matter, right? So this is sort of the blueprint that brings together dark energy and dark matter. And this model explains the structure and evolution of the universe from the Big Bang, so from the start of the universe, till now. And I'm sure you've heard of Einstein, Albert Einstein, who, by the way, actually did his PhD at the University of Zurich, where I'm currently
Come on.
studying.
I was gonna drop that fun fact, and I actually knew that one. You took my chance to shine away. Come on, man.
Did you know that because I told you?
No, I actually knew that because I watched Oppenheimer. And also like I just kind of knew in general because like there's like a couple like basic things that I think like some people know about like physics when they learn it in high school, and that was one of the things I learned. And I know there's also I don't think it's Marie Curie, but I think there's someone else who got there who studied at University of Zurich who's a pretty big physicist. I don't think it's Marie Curie.
It's not
She's
Mary
not a
Curie.
physicist. Yeah. Who is it?
It was actually, so he didn't study at the University of Zurich, but Schrödinger from Schrödinger's cat was actually the head of the physics department at the University
Oh,
of Zurich.
okay, Schrodinger's cat. That's right. Yeah, the scenario where if you open the cat, is your cat like if you put a cat in the box, do you know if the cat has really left the box if you until you open it? And the opening it is what the catalyst is pretty much to knowing if it's still there or not. And you can take that scenario to other aspects of life, like you know. I like Schrodinger's cat. I know we're talking about dark matter and energy, but I like Schrodinger's cat 'cause it's a good way to live life. Like you never really know if something is there unless you don't know if the cat's there unless you open the box. You don't know if something's there in your life unless you go and see that thing with your own two eyes. Because then that's the catalyst of okay, yes or no. Like, is the cat in the box, or is the cat out of the box?
Yeah, and
So
that's what Schrödinger was saying, you don't know if the cat is alive, if it's in the box or whatever, unless you see it with your own eyes. And the question more so was, does it actually exist, or do things exist upon us observing them? That's what Schrödinger was kind of saying. But yeah, going back to Einstein, right? So in 1917, he added a term called the cosmological constant, to his equations to keep the universe static. Because, like I told you, initially we had thought, up until the 1920s, up until Edwin Hubble, we thought that the universe was static, that it wasn't moving. And at the time, everyone believed the universe wasn't expanding or contracting. So Einstein adjusted his equations to match this view. So he added this cosmological constant to his equations to match what everyone else was saying, that the universe is static. But when Hubble came around and discovered the expanding universe, Einstein called the constant his biggest blunder. So he admitted that he had made the biggest mistake of his life, and he regretted it because he realized, he was like, how could I have made such a big mistake? And he called it his biggest blunder. And this is something that went down in physics history. This is something that we study.
Ratioed. You just got ratioed, bro. You just got ratioed. He had this whole constant equation that kept the universe constant, and then someone would just like, yeah, that's just not a thing. And imagine being Albert Einstein, the greatest, like one of the greatest modern day physicists of all time, and he's just like, well, L, like what do I do here? I just took an L.
It was an L, I would say. He did, like I said, it was a pretty big L. But people ended up coming around to this idea of this constant. So decades later, so quite a bit of time after, scientists actually realized that this constant could describe dark energy, just maybe not the way that he wanted it to. And dark energy, which is the force that is behind this accelerating expansion. So what Einstein thought was his biggest mistake actually turned out to be one of the most profound insights in cosmology.
So it wasn't an L for him, but not an L for the space overall, or I guess the scientific space overall, right?
Yeah, I don't think, yeah. Because anyways, like, isn't it important to learn from your mistakes? And this is what happened. Yes, maybe he called it his biggest blunder, but end of the day, we were able to learn a lot from this, this cosmological constant.
Good job, Mr. Einstein. I'm proud of you. He has cool
And
hair too.
he did have pretty cool hair, yes.
Yeah, and I like him because he was an absurdist.
What do you mean he was an absurdist?
Like, do you know the way that, like, how some people live life through, like, realism, stuff like that, different like philosophies on life. So
Yeah.
it's a philosophical theory, absurdism, and that that the universe is irrational and meaningless. And I don't think he thought it was meaningless, but like it's like absurdism is like the universe is irrational, meaningless, and like humans are in conflict with it when they're trying to find meaning. And I kind of like think that he's kind of like that. He kind of believed that because, I mean, he was just trolling half the time. Like, besides when he was doing his work, like the dude just used to like stick out his tongue at the camera in any photo. Like, he was just trolling people. Like, he used to just have fun. I think that's kind of a bit absurd. Like, it's just a bit of an absurdism in his everyday life. So I like him because of that. Maybe it might not be absurdism, but dude's just kind of like playing games and having a good time. And he was doing all that while like making some of the most like, important scientific discoveries of our generation. So like, I don't know. I think that's pretty baller.
Do you think that studying the universe, right? Because that's what he was doing, studying the universe, realizing that this place that we live in is so much bigger than we think, made him realize that, made him be more true to himself, because he realized, end of the day, it really doesn't matter. We're all just, floating around in space. So maybe that made it easier for him to sort of just be himself and not really care what other people think, because end of the day, there's so much more going on than that.
My guess would be that because he understood how vast the universe was, he realized how insignificant he was as a human. Like, this is how I look at it, right? Like, because I think I have a similar outlook in that sense, right? Like, because I understand how infinitely large our universe is, and how, like, although I love my life and I love the people in it, and I think the people in my life are very significant to me, and I care a lot about them, and I think there's a lot of things in my life that are very significant to me that I care about. I think in the grand scheme of humanity, I'm not even a speck of dust. And I think that's why it's important to like be true to yourself and live the life that you want, because at the end of the day, like you said, like with the universe infinitely expanding, there's only going to be more. Like, why would I use my not meaningless existence, but my such a minuscule amount of existence in this world that no one can like it's not even comparable to like you can't even understand how small you are in the grand scheme of things. That why would I use that in a way that I don't want to live my life? And I think that's probably how he understood things as well. Like there's no point to wasting time doing something that you don't like or that doesn't challenge you in a way that you want to because like you only get one shot at this, you know, this one way at life to kind of do my thing, you know, and have my fun. I think that's something that's I wish more people were willing to kind of try that mindset because you know I'm no physicist by any means, but I think that I grew up in a really cool way where I was able to stay very present and be aware of how not insignificant I was, but like how, like I said, like small I am, and I can make myself larger in one way or another. But like at the end of the day, no matter what, in 200 years, very, very, very few people will be remembered. In 1,000 years, even fewer, you know, from our generation. So I think it's important to just live the life you want to live and you can kind of move on and do your own thing after that. You know what I mean? And I think he probably saw some of that too and recognized that in his own life.
Thank you. That was very inspiring. So we're
Happy to
almost,
have.
we're almost at the end here. And I just want to sort of like wrap up this idea of dark energy, and then we're going to come to something that I think you might find is pretty cool. So dark energy. To picture it, like I said, we thought about the balloon, right? We're blowing air into it, and the points are sort of like moving away from each other. And not only are they moving away from each other, but rather they're moving away from each other at an accelerated rate, right? And so dark energy works like those hidden pumps. It speeds up the expansion of the universe over time. So one idea is that dark energy is a property of space itself, and every bit of space has energy, so that as this balloon stretches and creates more space, there's more dark energy driving even faster expansion, right? And if dark energy continues to dominate, galaxies will drift further apart, and billions of years from now, the night sky could go dark as distant galaxies fade from view. And this is called the Big Freeze. So it's where the universe becomes a cold, isolated expanse, and these galaxies are really far away from us, and it makes everything turn dark. But we're still learning, and like I said, nature hasn't been very kind to us, so there could still be a couple more surprises waiting for us at the end of this discovery. So that's dark matter, that's dark energy, and sort of coming to now this really cool thing that I wanted to show you, which is, have you heard of the Euclid Mission before?
No, it sounds like ukulele, but tell me about it.
Okay, so first of all, just because you said it sounds like ukulele, which it isn't, the name Euclid honors the ancient Greek mathematician Euclid of Alexandria, and he was renowned as the father of geometry. His work laid the foundational principles of geometry, which are integral to understanding the spatial relationships that the Euclid spacecraft examines in the universe, right? So what is the Euclid mission? It is a mission that was sent out by the European Space Agency. And here's the cool part. It has contributions from Durham University, where we both graduated and met, and the University of Zurich, where I currently study, which is why it's very cool. And it was launched by the ESA in July 2023, and it aims to investigate the enigmatic components of our universe, dark matter and dark energy, which I just finished explaining to you, by mapping the large-scale structure of the cosmos. It's pretty cool, right?
All I know is I feel like I'm the father of geometry, you know? No, but shout out to DU for the big help and discovery there. Shout out to Durham, man.
Actually, one of the founders of the Euclid Mission, Richard Massey, was my theoretical physics professor in my second year at Durham, and he worked on this mission for the past 20 years.
Damn. So he's committed his life to this.
He did, yeah.
That's pretty That's pretty baller. I was gonna say a different word, but I don't know how like how language friendly this podcast can be, but that's pretty BA. That's pretty baller, like that's cool.
So that is it. We went over dark matter, which makes up 27% of the universe. We went over dark energy, which makes up 68%. And we're continuing our search for these things to try to understand them. And the cool part here is, how do you say in American terms, our alma mater, our alma
Alma
mater,
mater, yeah. Alma
alma
mater,
mater,
yeah.
yeah. Yeah, has contributed heavily to this, which is pretty cool, I think. I hope you feel like you've learned a lot today.
I feel like I've gotten educated quite a bit. Yeah, definitely learned a lot. Definitely good talking to you. Nice to learn a little bit about dark matter, dark energy, Mr. Euclid and his mission, how he's the father of geometry, and who knows, maybe I'll go swimming in a pool of dark energy and dark matter at the same time, even though they're not the same thing. But no, I definitely had fun. This is super educational. I feel like I got my mind blown like once or twice. Like definitely cool perspectives to have, and my favorite part was talking about Einstein. You know, talking about the beast himself.
You
Well,
really
thank
like
you for,
Einstein, huh?
yeah, that's my guy. That's my guy for sure. Um, but thank you for having me on the show, Miss Yamani. I've had lovely time chatting with you. Best of luck on your next endeavors, and hopefully I'll be a guest on this show again soon.
Thank you for being brave enough to cross the bridge. Or rather, like you said, you would have crossed the bridge anyway, but thank you for, letting me be the one who, to sort of help you cross this bridge in the first place.
Absolutely, absolutely. Again, like I said, you expanded my mind, and I'm happy to be here. And now, for the end of the episode, I'm gonna give a plug to myself. Everyone, if you don't like having tickets scalped and having tickets be super expensive, go check out Toutix.com. That is my ticketing business. We're building a marketplace that's gonna eliminate scalping and give equitable returns to everyone involved when you resell a ticket. And we're trying to make the first fan-friendly, artist-friendly, and like event organizer friendly ticketing platform there ever was, and cut out the middleman who makes so much money off of your backs by scalping tickets. So check out Toutix. If you have any questions, feel free to message me on LinkedIn. Always here to help. Thank you for having me, Bernard.
Thank you for being here. And a quick shout out to your co-founder Daniel, who also graduated from Durham University, who is also a physics major in my class. So yeah, thank you for your time today.
Thank you. Shout out Danny. Talk to you soon.